Finally, the last aspect on the periodic table where we learn about more information that is hidden in the periodic table and not directly conveyed. Sure, on the periodic table we can look for the symbols of the elements, their atomic numbers, their atomic masses, their group numbers, and their period numbers. And we can even deduce the electron configurations. But then there are trends in the periodic table. Trends like what is the direction in terms of the size? Is it increasing or decreasing, going one way or another? There are four trends to be exact: the atomic size, the ion size, the ionization energy, and the electron affinity. We will look at all four of them in this video. Atomic size increases moving down from top to bottom of a group. The valence shell is higher in energy and farther from the nucleus, traveling down the group, while the atomic size decreases from left to right because the increase in magnitude of positive charge in the nucleus pulls the electrons closer to the nucleus. Well, let's have a look here. These are the sizes of the atoms. Uh, in this version we have missing elements in the first period, but you might think that hydrogen might be the smallest element, but it's not. The smallest element is on the right side of the periodic table, and that's helium. And you might think that the largest might be here, but it's not. The largest is on the lower left, cesium. Why is that the case? Well, let's answer why does the size decrease going from left to right when in fact the number of protons, neutrons, electrons are increasing. The reason is as we go from left to right, we are in the same principal energy level first of all. So for example, here this is principal energy level number 4, which is period 4. While remaining in the same level, the number of protons in a very small region of the nucleus keeps on increasing. Well, that doesn't have any effect on the size because it's very dense, very small, tiny region in the center. But even though we are increasing the number of electrons, those electrons don't carry any mass. They don't occupy more space. On the other hand, now we have greater amount of positive charge in the middle and greater amount of negative charge surrounding it. Well, now there is greater force of attraction between the two. Remember, a magnet, for example, has the north pole and the south pole, and they are attracted to each other. But if you have a small magnet with a small north pole, south pole, or a large magnet with a large north pole, south pole, the attraction between the poles of the large magnet will be much stronger than the attraction between the poles of the smaller magnets. And similarly here, as the charge difference increases, uh, whatever is the total protons here and the total electrons here, over here we have way more protons and way more electrons, uh, 18 more exact, going from here to here. So now they are much more strongly attracted, and that pulls the electrons to the center where the nucleus is. That's why the trend is going to be that the size decreases going from left to right. There are always exceptions like you see here, but we are talking about a trend. Within a trend there are always likely exceptions, but the general movement is in a decrease in the size. Going from top to bottom, why does the size increase? Because we are moving from one period to the next. It's like jumping from one floor to the next floor. As we move to the next period, the principal energy level is greater, and hence the electrons are further out, and that's why the trend from top to bottom is the increase in size. So this is the size of atoms. Cation size and anion size, there is a trend there as well. Cations are smaller than their parents. More protons than electrons creates an increased nuclear charge, and extra protons pull the remaining electrons closer to the nucleus. So if I ask you, you have the iron atom, then you have the two, well, if you, let's not forget about iron for a second, but let's say you have sodium atom, and then you have Na1 plus cation. Which one will be larger, the atom or the ion, the cation? The atom will be larger because now in Na1 plus you have 11 protons but only 10 electrons, which are even pulled further closer to the nucleus, because now there is extra proton power to pull the electrons closer. Here you have two ions, Fe2 plus, ion 2 plus and ion 3 plus. Which one will be smaller? The one with more positive charge will be smaller, because the number of protons does not change in either of them. Because we have reduced the number of electrons, one more here than here, the remaining electrons are pulled even more tightly to the center. Anions, on the other hand, are larger than their parent atom. Because we have more electrons than the protons, the excess negative charge reduces the pull of nucleus on each individual electron. So if we had originally 10 protons and 10 electrons, and then we have 10 protons but 11 electrons, that last electron, which gives that ion a 1 minus charge, is only being pulled by 10 protons. It's not being pulled by 11 protons. It doesn't experience the same level of pull that it would otherwise. Hence, it spreads out or moves farther away from the nucleus. And that's why the size of the anion will always be larger than the original atom. And here are some of the examples: the lithium atom and the lithium ion. See how much is the size difference. The numbers here stands for picometers, which is the size given the metric unit pico, and 152 picometers and 74 picometers, 186, 102. So as you can see, the sizes are much different, and the positively charged cations are always smaller than their original parent atoms. On the other hand, here you have the original atoms on the left, which are smaller than the ions, the anions, as you see here. Ionization energy is the energy required to remove an electron from an atom. Mostly we remove electrons from metals. Well, because there is attraction between the protons and the electrons, we need to supply energy to remove an electron from the atom. And for example, sodium metal doesn't just give up one electron without a fight. It requires energy that we use to remove an electron, and that energy is called ionization energy, energy required to remove an electron from an isolated atom. The magnitude of this energy is directly correlated with the strength of the attractive force between the nucleus and the outermost electron. Whenever we are removing the electron, we are talking about removing the outermost electron. Remember, in the electron configuration of sodium 1s2, 2s2, 2p6, 3s1, we removed the 3s1 electron, the outermost electron, so that it would have the electron configuration of neon. The lower the ionization energy, the easier it is to form a cation. So let's look at the trend for the ionization energy, and it might look messy here, but it will soon make sense. Ionization energy decreases down a family, meaning it decreases going down a group, and it increases across a period, meaning going to the right it increases. Why would that be the case? Why would it decrease down a group and increase across a period? Well, as we go down, we are stepping into larger and larger principal levels, farther away from the center. The farther away we go from the center, the less the electron that's on the very edge, the outside perimeter of that atom, feels an attraction for the center, because the protons are that far away. As a result, it's very easy to pull that electron away. That's why the trend is that going from top to bottom, the ionization energy, or the energy required to remove an electron, decreases. But as we go from left to right, we learned that how the size gets smaller, because the protons are more strongly able to pull the electrons, where similarly, if they are so strongly able to pull the electrons, we will also have a hard time to pull away an electron, and so we have to supply more energy to pull away an electron. Hence the ionization energy increases from left to right. That's what you see in this chart. And for example, Lithium is in period 2 and going to the neon atom all the way on the right in period 2, the ionization energy trend is increasing from left to right. But then as we drop down to period 3, we suddenly see a drop in the ionization energy, and then we climb again all the way to argon and so on. Electron affinity finally is the energy released when a single electron is added to an isolated atom. So we learned how nonmetals want to gain electrons. Well, nonmetals, when they gain electrons, they don't require energy. Rather, they release energy. When they release energy, we write it on the right side of this form of equation, which we will talk about starting in next chapter. Okay, so energy is released. And so we call it electron affinity, and electron affinity gives the information about the ease of formation of the anion. Large electron affinity indicates an atom becoming more stable as it forms an anion. What's the trend? Electron affinity generally decreases down a group, going from top to bottom, and electron affinity generally increases across a period, going from left to right. And that makes sense because as we go from left to right, we have non-metals on the right, and non-metals are the ones which want to gain electron to look like the noble gases, to achieve the noble gas configuration. So they would be more stabilized, and hence electron affinity, or affinity means friendship or love for electrons increases from left to right. On the other hand, electron affinity generally decreases down a group. The metal becomes even more metallic, and it's easier to remove an electron going down, and so the ionization energy decreases, while electron affinity, or the love for electrons, extra electrons, also decreases. And that's what you see here. The trend for electron affinity is not as neat as the trend for ionization energy, but you can read this and you will still find that trend in here.